Oh, yes. Thanks, Javon, for your very kind introduction. And I also would like to thank the organizers for their very kind invitation. So today I want to maybe report something about the geometric properties tropical polytopes and how they can be used for studying tropical tensors. Okay, let's start from some basic definitions of tropical tensors. So in this talk, we are working over the tropical semiring, which means we work over Rx. It is a union of the real numbers and the negative infinity, and we redefine the addition operation by so x plus y is just taking the maximal of x and y, and x times y is just x plus y. And the neutral element for this tropical semiring for the addition operation is negative infinity, and for the multiplication is the zero element. Okay, similarly, we can define operations for tropical matrices. So here, a tropical matrix means every entry is taken from the tropical semiring R max. So A plus B, the ijth entry of A plus B, just taking the maximal of Aij and Bij, and the product of A and B is just taking the maximal of all the pairs of summation Aik plus Bkj. So here we can also study the scalar action. For example, lambda acting on a vector V just by adding the scalar lambda to each entry of this vector. Then after these definitions, we can speak about eigenvalues and eigenvectors of tropical matrix A. So they are just solutions of A times V is equal to lambda plus V. And similarly, we can define eigenvalues of tropical tensors, and also maybe singular vector tuples of tropical tensors. So in this talk, I will perhaps just state our results for tropical matrices. So some results can be generalized to tensors. I think all the results can be generalized to tensors, and some extension is straightforward, and some extensions maybe non-trivial. But because here we just want to see the intuition and the method, so I just focus on tropical matrices. Okay, so why do we care about tropical tensors? In fact, tropical tensors arise naturally in many areas like optimization, game theory, approximation theory, and so on. Maybe let's start from a baby example. So for example, we are given a direct distance matrix A, and we want to find the longest distance. So here by a direct distance matrix, we mean each entry Aij gives us the distance from node I to node J. For example, let's say the distance from Paris to LA is 11 hours flight, and but if we want to make one connection, so for example, we have several choices. Like if we want to make a connection at Chicago, then the distance is equal to the distance from Paris to Chicago, maybe 8 hours, and from Chicago to LA, maybe a 4 hours flight. So the distance is 8 plus 4. And we can also make a connection, let's say at Beijing, it's from Paris to Beijing, it's maybe 10 hours flight, plus the distance from Beijing to LA, maybe 12 hours. So we just take the maximal of this distance. So this value is exactly the ij entry of A square. So if we want to find all the longest paths allowing any number of connections. We just sum all the all the powers of A together. So here maybe we can look at a slightly more complicated example. It's called the market of invitation to tenders. So here we have a decision maker and we have N companies. And the decision maker call for invitations to tenders from these companies. For each invitation J, company I will ask for the price Pij, and this price matrix is publicly observed. So the decision maker wants to choose the best offer. So here the best offer depends on two factors. The first one is the price matrix, and the second one is some hidden information. It's some estimate of the technical quality of each company, but this is only private to the decision maker. The other people don't know. So what the decision maker do is he wants to minimize the expected cost, which is the minimal of a Pij divided by Fi. So here we can see that the larger Fi, the better technical quality of the estimate of company I. Okay, so in fact, after several rounds of bidding prices or several rounds of invitation to tenders, the market of these prices will reach some equilibrium, namely the minimal of the cost will be achieved at least twice. Why? Because, for example, let's say Pij divided by Fi is strictly smaller than any other Pkj divided by Fk, then the company I can raise the price a little bit, such that this company still wins the offer. So because company I wants to maximize his interest, so he continually raises the price until this term equals to another Pkj divided by Fk. So that means, so finally the market will reach some equilibrium. So after some change of variables, the above equilibrium can be formulated as the maximum of some tropical matrix Vij plus Ai is achieved at least twice. So we will see later, in fact, this means for each J, the column Vj of this matrix V lies in some hidden hyperplane HA, because those companies want to maximize their interest. So it will be important for them to statistically infer the hidden information A from the known tropical matrix V. Okay, so hopefully I hope maybe we are convinced that tropical tensors arise very naturally in our daily life. And in fact, given tropical tensor, we would like to do some data analysis for this tropical tensor. Maybe in this talk, we will just treat the two simplest example. The first one is a tropical linear regression. Namely, we also given some training data, we want to find a hyperplane which best fits this training data. And the second method is for a given tropical matrix, we want to find a best rank 1 approximation. So before presenting our results, let's recall some definitions. It's very similar to the classical case. So for example, what is tropical convex cone? So C is called a tropical convex cone if it is a scalar invariant, and also for any two vectors inside of this tropical cone, the summation of these two vectors is also contained in this cone, in this subset. And for any given subset inside of the ambient space, we can talk about the tropical cone generated by this set, just the set of all the supremes of scalar plus vectors inside of this set. And like the classical case, we will be working over the projective space. Here, it means the quotient of the ambient tropical vector space by some equivalence relation. So here, x is equivalent to y if and only if x minus y is a constant. Since we want to study approximation theory, so it's better that of course we need some metric. So a very natural metric on the projective space is the Hilbert projective metric. It's defined by the maximum of the coordinates minus the minimum of the coordinates. And given two subsets inside of the projective space, we will measure the Hausdorff distance from A to B by just first taking the infimal over B and then taking the super over A. Okay, so then now we define a tropical hyperplane. So given a point A inside the tropical projective space, the tropical hyperplane is defined to be the set of vectors such that the maximal of AI plus xi is achieved at least twice. So here is some geometric illustration. Since here the projective space is invariant under scalar multiplication. So to visualize this HA, we just we just project everything onto a hyperplane which is perpendicular to the vector 1, 1, 1, and inside this hyperplane HA, the image of projection of HA is looks like a union of these three half lines, and this vertex is minus A, and this vertex will be called the apex. In fact, the tropical linear regression problem can be formulated as finding the infimal of the distance, Hausdorff distance from a given subset V to the hyperplanes HA. Okay, so yes, so how should we relate it to inner radius? So the first, the inner radius of a given subset V is defined to be the supreme of R, such that there is a finite vector V and a Hilbert ball centered at B with a radius R contained in the tropical convex cone spanned by V. It turns out, in fact, the infimal of the Hausdorff distance from the subset V to the hyperplanes is equal to the inner radius of this subset, which means the tropical linear regression problem can be reduced to finding the inner radius of the subset. Okay, now the problem is how to compute the inner radius. So we will use some tools from game theory. Let's recall what is zero-sum two-player deterministic game. So given a tropical matrix V, so we have two players, so player min and player max. So starting from state I, so player min goes first. He will choose state K such that VIK is finite. And then it's turn for player max to play, and he will choose the next state, which is different from I. Okay, and then so in fact, after this step, so player min will pay some payment to player max, and the amount of the payment is equal to negative VIK plus VJK. So here, by the way, why we call this player min? Because he wants to minimize the payment, and this player max, he wants to maximize the payment he received from player min. Okay, so here a strategy means so every step how these two players choose the states. So after L terms, let's say if they choose the sequence of actions to be I, K1, I1 up to KIL, IL, in fact, the total payment is just the summation of all the payments in each step. Because player min wants to minimize the payment, and player max wants to maximize the payment. So finally, when they reach the agreement, that means we can show the mean of max is equal to max min. But when this agreement reached, this payment is called the value. Okay, now so we can associate a Shapley operator to this two-player zero sum game. It looks a little bit complicated, but we don't need to remember. We just need to know we have a two-player zero sum game, and min wants to minimize the payment, and the max wants to maximize the payment. And when they reach the agreement, the payment is called the value. And also by theorem of Shapley, in fact, this value is equal to, we evaluate this Shapley operator at 0. Okay, so if we allow the horizon to be infinite, in fact, the sequence of TL evaluate at 0 divided by L, this sequence has a limit, and this limit is called the mean payoff vector, and the above process is called the mean payoff game. We know the computational complexity of computing this mean payoff vector is in both NP and CoNP, and later we will use a variant of this known valuation iteration algorithm to compute this one. And for our case, in fact, the mean payoff is always non-positive. Okay, so why it is related to the inner radius? So here, in fact, we can show that the inner radius of the column space of a given tropical matrix is equal to the negative of the spectral radius of the associated Shapley operator. Moreover, if A is some here, let's say it's a sub eigenvector. In fact, we can find the best hyperplane HA from this sub eigenvector, and if B is some super eigenvector, of course, so we can find the corresponding Hilbert ball contained in this tropical polytope. So as a corollary, we will get that the tropical linear regression problem is a polynomial time equivalent to mean payoff game. So here is a geometric illustration. Let's say we have a 3×4 tropical matrix V. So here so here I just label by red dot these 4 columns, and we want to yes, and here the gray area is the tropical convex cone or the tropical polytope band generated by these 4 vectors, and the black area is the maximum Hilbert ball contained in this polytope. And here we can see that the center of this ball, in fact, gives us the apex of the best hyperplane approximating these 4 vectors. Okay, and everything can be computed by can be computed as eigenvalue problem. Okay, now we can revisit the problem of equilibrium of the market of invitation to tenders. So just recall that in fact, after a change of variables, the equilibrium is just it's just the maximum of Vij plus Ai is achieved twice. That means each column of matrix V is inside of a hyperplane HA. But in fact, in practice, if we have many rounds of bidding price, they cannot lie in a hyperplane. So what we do is we want to find the best hyperplane approximation, which is just our tropical linear regression. Okay, so from the above theorem, we see that the tropical linear regression problem is just to finding the negative spectral radius, and the best hyperplane is achieved by the corresponding eigenvector. So yeah, we can use a variant of the valuation iteration algorithm, and here yeah, I think maybe it's easier to look at this picture. So here, let's say we have 3 companies, and we have 100 invitations to tenders. So here I just label by right dots all these cases. So by running this algorithm, we can find best hyperplane which best fits this training data. And here we can see that in fact this hyperplane divides the whole space into 3 areas, and inside of this sector, in fact, all these points are the cases where, let's say, a company 1 wins the offer, and similarly here, these are the cases where company 2 wins the offer. Okay, and so for the above value iteration algorithm, we can also study the complexity. In fact, so let W to be the maximum of the Hilbert norm of the vector of the column vectors of the tropical matrix. So the above valuation iteration algorithm only can compute the epsilon approximation of the inner radius in n times p times w divided by epsilon arithmetic operations. In fact, this is a theoretic upper bound. In practice, the algorithm is super effective. In fact, yes. For example, for this, yeah, yes. So we have 100 invitations, and usually when we do experiments, we only need maybe 20 or 30 iterations to make the algorithm converge. So it's super effective. Okay, so now we talk about the best rank 1 approximation. So first, we relate the best rank 1 approximation to the outer radius of a subset inside of the tropical ambient space, which is infimo of R, such that we can find some finite vector B and Hilbert centered at B with radius R containing the tropical polytope spanned by B. It turns out this outer radius is nothing but twice of the distance from the matrix V to its best rank 1 approximation. So which means if we want to find a best rank 1 approximation of this matrix, we only need to compute the outer radius of the span of the column space of this matrix V.
So Yang, you have 5 minutes to go.
Yeah, yes, thanks. So just introduce two notations. So for any tropical matrix A, we define A star to be the summation of the identity matrix and all the powers of A. And with a finite matrix V, we will associate V with new matrix H, which is the product of V and the minus V transpose. We can show, in fact, that this new defined matrix H has a unique eigenvalue, and this eigenvalue is exactly the outer radius of the column space of the tropical matrix V. Moreover, all the centers of the Hilbert outer balls of the column space of V is will form the column space of this matrix. It's negative lambda times the identity matrix plus H star. Okay, so by this theorem, we see that to find the best rank 1 approximation of tropical matrix, we only need to compute this unique eigenvalue of H. So combinatorially, this is given by the max cycle mean, or by algorithms, we can still run the value iteration algorithm as before. Okay, so here is an maybe a functional case of rank 1 approximation, and I want that I will. It's also some maybe application in approximation theory. So here, if we have some functions defined on x times y, so here x is some compact metric space. Y is non-empty, and we suppose that the family of functions vy is actually continuous, then to study this best rank 1 approximation. So that means for this function, we want to approximate by a summation of x fx plus gy. In fact, this functional best rank 1 approximation problem can achieve optimal solution, which is equal to 1/2 of the tropical eigenvalue of this new defined function H. And also this F is a tropical eigenvector of this function H. And once we know F, we can compute G. Okay, so hopefully so in this talk, we are convinced that the tropical tensors arise naturally in applications, and maybe it will be interesting to do some data analysis for tropical tensors. And in particular, tropical linear regression problem is equivalent to finding some inner radius, which is polynomial time equivalent to some mean payoff gain. And for finding best rank 1 approximation for a tropical matrix, it is equivalent to finding the outer radius of the tropical polytope spanned by those columns of the matrix, and this problem can be reduced to the eigenvalue problem. That's it. Thank you very much for your attention.